real life.
Okay, thank you for the introduction. So today I will try to present our recent work on the interior point method for solving frictional contact problem and the use of continuation techniques to try to find solution when the problem is non-contact. So it's a joint work with Paul Armand and our PhD student, Aung Min Nguyen. So, okay, just we'll start with some very standard notation. So I consider to have a contact between two bodies. So just for one contact, I define the gap function, so the sign distance between these two possible contact points. Local reaction forces and velocities are decomposed into a local contact frame defined by the normal n and tangential vectors. And in this setting, so I want to improve the Signorini condition first at the position level. So the gap function has to be positive, the contact traction has also to be positive, and the product of both is equal to 0. So the meaning of this perpendicular sign, so sorry for that, I am colorblind, so I'm not able to see the pointer, but since it is here, means that Gn times Rn is equal to 0. And I will use, in fact, this condition at the velocity level, considering un, so the normal velocity, and I will consider the condition at the velocity level. So un has to be greater than 0 if we are in contact, and Rn is also greater than 0. And if you are not in contact, Rn is 0. Now some notation for the Coulomb friction. So very standard notation. So I introduce the Coulomb's cone, which is a second order cone. So the Coulomb's cone is all the reaction are in R3 such that the norm of the tangential reaction is less than mu, the coefficient restriction times the normal reaction forces. And Coulomb's law postulates two cases, sticking case. In that case, the tangential velocity is equal to 0 and R has to be into the cone. And the sliding case, where the norm of the tangential velocity is different from 0, is positive, and Rn, Rt, let's say R is on the boundary of the cone. So Rt, the norm of Rt is equal to mu Rn. So with the contact condition, you can enumerate all the cases. You can have no contact, takeoff, sticking, or sliding. And if you use this disjunctive formulation of contact and friction, it's convenient if you have one contact, but you cannot solve large problem with a lot of contact. Otherwise, you have to enumerate all the cases. So I will try to reformulate contact and friction using tricks that come from Jerry de Saxe. And in fact, I will use this modified relative velocity u tilde. So the modification is that I had mu times norm of ut just in the normal direction to be able to formulate a complementarity problem. So in fact, we know that friction is does not satisfy normality conditions, so the relative velocity is not normal to the cone when we slide. So in that case, u tilde is modified such that it will be normal to the cone. So if I introduce dual convex zone to K, I'm able to get the 7, so it's equation 7. So a complementarity condition between u tilde and R, so u tilde and R are perpendicular. U tilde is in dual cone and R in the Coulomb's cone, okay? So thanks to this formulation, I get a second order cone complementarity condition, and then I will be able to use techniques from optimization to solve this problem. Okay, so this formulation is completely equivalent to write variational inequalities, but complementarity problem is a subclass of variational inequalities that are a little bit better to do numerics. Okay, so it's just a sketch of the Coulomb friction. So just the important point when you slide. So R is on the boundary of the cone. The velocity u is in the tangent plane when you slide, and u tilde is normal to this cone. Okay, now I will introduce, let us say, a quite general discrete frictional contact problem. So I have my complementarity condition between u tilde and R, the definition of u tilde, sorry, here, and two other relations that will relate local variable R and U at contact with the generalized velocity of my problem, okay? So you can consider that this problem comes from time and space discretization of your dynamic problem, but it can also be used in the quasi-static setting. And M is assumed to be symmetric positive definite matrix, and all the other data, there is no real assumption on it. So why using this problem? So I think that this problem is generic enough to include a large number of applications, so in quasi-static, dynamics, whatever the space discretization that you use. At least in the linear case, it is quite representative of the problems that we have to solve if we want to solve contact and friction problem at each time step or each load increment. And but it is linear in some sense, so but it can be used inside the Newton procedures if you want, if you linearize the systems. And just I want to mention that this problem can be reduced on the contact variable. So just by computing the inverse of the mass matrix, you can have this type of formulation. So U is related to R through the matrix W, which is called sometimes the de Lassus matrix. Okay. So, but from the numerical point of view, we prefer to keep the sparse large structure, the previous problem. Okay, as I said before, so this problem is a finite dimensional second order cone complementarity problem, so or variational inequalities. But it is not really a standard one, you know, just due to the fact that we have this matrix. Sorry, we have here this J function, and this J function is just a modification of my velocity to retrieve normality condition. Okay, so and one of the difficulty in this problem is the fact that J is non-smooth, so it contains a norm, and it breaks completely the monotony of the problem. So if J is equal to 0, we have a monotone variational inequality, everything is fine, but we are in the case of associated friction problem, which is not really really useful in practice, but because when you slide, then you take off at the same time, so you have dilatancy. So the problem seems to be a nice problem from the structural point of view. We have a second order cone complementarity problem, but there is any result in the literature to prove that we can have convergence algorithm to solve that. Okay, so some remark about this problem just before to switch to interior point techniques. So the variational inequality is not the optimality condition of an optimization problem. So it is related to your comment just before, Patrick. So there is no minimization problem or simple minimization problem associated with Coulomb friction. There is some existence result under flatter assumption, so it's a feasibility assumption. So we know that we can check this existence assumption. There is a bunch of methods that come from mainly adaptation from methods from optimization and mathematical problem to solve such type of problem. But just to be really fast, we have a lot of first-order methods like fixed point with projection, non-smooth Gauss-Seidel method, augmented Lagrangian method. So they are quite efficient and quite robust, but really slow to get high accuracy. And if H is not full rank, as you can have in granular materials, for instance, or rigid multi-body systems, or even in beams application, for instance, you can have also H is not full rank, then we are not able to get high accuracy because we are not able to have second order convergence rate. So this is the reason why we try to use interior point techniques for this problem. Why interior point? Because it's a method that is really used in optimization to solve large-scale problem over second order cone. So how it can be adapted to frictional contact problem. Oops. So I don't know if you are familiar with interior point, so I will really explain that really quickly. So here is my original problem that I want to solve. So I don't know where is the button. So I've just rescaled the problem such that the cone are self-dual cone. So it's just a reparametrization of the cone. And here, the only difference is that you have the Jordan product between mu tilde and R to get the orthogonality. Why the Jordan product? Because we will work in second order cone on Jordan algebra. And what we are doing in interior point techniques is we relax this condition in that way by introducing what is called the barrier parameter tau. So this product is no longer equal to 0, but equal to 2 tau E, and E is a vector of 1. Okay? And the goal is to drive tau to 0, okay? If we drive tau to 0, then we will get a solution of the original problem. And the other tricks in interior point techniques is that the iterates of the method are in the interior of the feasible set. So the name interior point is that all the iterations are in the interior of the feasible set, and only at the optimality condition, we go to the boundary of the feasible point if one constraint is active. Okay, so in interior points, we try to solve this problem. So it's so for a given value of tau, it gives us a solution in terms of V, U, R, and S. And we drive tau to 0. So you can imagine that we are trying to follow a curve that is parameterized by tau up to tau equal to 0. And this curve is called the central path. Okay. Why central path? Because we are in the interior of the feasible set. And okay, in the convex set case, sorry, for instance, if S is given, so fixed S, for instance, this problem is a convex, is in fact the optimality condition to a convex set. Interior point techniques work quite well, very efficiently. We get second order convergence. Even if H is rank deficient, this problem is well posed. So now we will try to extend that to general frictional contact problem when S is not fixed. Okay, so we have some theoretical results that say under this Slater assumption here, so the Slater assumption is that you need to have V such that H times V plus W is inside the interior cone. So it's a feasibility assumption for our system. So under this condition, we are able to prove that, in fact, the perturbed problem has a solution for every tau, positive tau. So it's the first solution. And more of that, in fact, for tau, every tau positive, this central path is analytic. Okay, so it's a result that we get just with this assumption. And this assumption can be easily checked numerically, in fact. And you have just to solve a feasibility optimization problem. So how we prove that? So we use, in fact, we go back to a convex problem for a given S. Then we use fixed point Brouwer theorem on S to prove that this solution exists for every tau. And then to prove that the analytic central path, the central path is analytic, sorry, we use curve selection lemma from semi-algebraic analysis. Because in fact, this problem is a semi-algebraic problem. Okay, so in practice, in interior point techniques, so you want to solve the perturbed problem. How to solve it? You perform Newton iteration on it. Okay? So if you have to do some Newton iteration, so G has to be equal to this vector, and we perform Newton iteration on it. We compute the Jacobian. So you can see that, in fact, at each iteration, the Jacobian is constant. So there is a small trick about the fact that we have a norm. So we have normally to do the subdifferential for this norm to compute generalized Jacobian. And we solve these systems, and we use Merotra-like algorithm. So we have to solve for a direction D, G of D minus G, the residual, plus this term that is here, is equal to 0. So at each iteration of the algorithm, we solve these linear systems. We iterate like in the Newton method, then we update tau, and we continue like that. Okay? And I don't know, so it's quite technical, but in fact, we use very common interior point techniques that is called Merotra type algorithm. So first, you solve these systems the first time, you get an affine direction without the terms with regularization parameter. Then you adapt the value of tau, you adapt the value of sigma, and you solve, you do a correction. So it's a predictor corrector scheme. So I do not have time to enter into more detail, but it's quite classical in optimization to do that. So what happens if you use that or quite not so large systems, so less than 100 contacts? So it outperforms, in fact, first order schemes like NSGS or alternative direction method of multiplier, but it is quite efficient, it works well, but if we go to larger systems, it fails completely. Okay, so if we go to larger systems, then we are not able to solve, let us say, for a tolerance of 10 to the minus 12, we are able only to solve, let us say, less than 10% of the problem. And why? There is two main problems with the non-convexity of this problem. Is the fact that here you have a draw of the central path. You have just for one cone, so R and U, and I draw here the central path. You start from there, you go there, and then you slide on the boundary of the feasible point. 5 minutes? Okay. You slide on the boundary of the feasible point, and you go in the interior. And when you are there, you still really need to do very, very small time step. Otherwise, you go out of your visible domain, and then the algorithm stops. Okay, this is one of the problems that we get, and this problem is quite common. So it's, let us say, I want to say that's a generic problem. So this is the first problem that we have, and most of the time, so the algorithm stops here, and we get some kind of fake solution. At least the contact status is not good. And the other problem, so let us say that this problem can be fixed by using very small time steps. So it is costly, but it is expensive, but we are able to find a solution. The other problem is this one, is the fact that here, sorry, you have a draw of the central path up to this point, and we go to the solution like that for one cone. So there is another zoom on this central path. And what happens is that this central path is monotonically described up to this point. So when tau decreases, you get this point, and then tau has to increase again to go to the solution. So the central path, there is some result in the convex setting that says that the central path is monotonically parameterized by tau in the convex setting. This is not the case in the non-convex setting with column friction. So since in the algorithm, standard algorithm, you want to decrease tau at each iteration, it doesn't work, okay? So just how to solve that? So we decided to use the continuation techniques to solve that, to follow the central path with the continuation so that we are able to increase tau if needed and then decreasing tau if needed. So tau is not forced to decrease, but is now an unknown of our problem. So just some very quick word how works these continuation techniques. So in fact, we rewrite all the systems into a quadratic form. So here you have a linear operator, a constant vector, a bilinear form, and then we get a bilinear form for the problem. So this problem is completely equivalent to the previous one with this type of operator. And then we do a Taylor expansion of the central path. So we know that the central path is analytic. We do a Taylor expansion, and we compute all the terms of the series, okay? And fortunately, in our case, the Jacobian, for all the terms of the series, the Jacobian is constant, so we have just to invert one time the Jacobian and compute, yes, the n terms of the series. So I will not enter into detail, but it is quite easy to compute all these terms, so you get it. But the most important stuff that I have to mention is the fact that tau is also parameterized as a series. And we are able to compute the radius of convergence and to know where the series is valid. And then what we get is such type of, of evolution of tau. So tau is decreasing, so each dot is a new computation of the sequence, of the series, It's decreasing, and sometimes it is increasing and goes to 0, okay? So we follow exactly the central path. This is exactly what you see here. So in red, you have decreasing tau, and in blue, increasing tau. And with that, at least for small problem, less than 10 contacts, 100, 1000, we are able to solve all the problem at the machine accuracy, and we have still some trouble to go for larger problem. But we are working on that. This is mainly due to numerical accuracy. Okay, it's time to conclude. So I think it's a promising way to solve contact and friction with high accuracy and second order convergence rate with IPM and numerical methods. For the moment, it is quite expensive, but we try to work on hybridizing standard IPM and this type of approach, and to try to extend that to plasticity and fracture also. Thank you.
Very quick question, while the next speakers
understand the original problem, the two-vector force and velocity has the orthogonal condition, so the dot product equal to 0. And then on the perturbed problem, like now it's not equal to 0. Is that somehow this method remove the orthogonality? Or this method exclude the case of sliding?
The case of sliding is not excluded. Okay, you get it. The only equation that you relax is the orthogonality. Okay, and if you exclude this this term, the orthogonality, and if you are in the interior of the set, then these equations are, let us say, nonlinear equations that you have to solve. It's clear, but you have to stay inside the interior of the set, and only the convergence you are on the boundary of the set, and then you have, let us say, you can say that sliding. See your question? Oh, okay.
Thank you again.
Thank you. Oh. I have to be careful.